Hi everyone. The goal of this video is to identify the structure of a polynomial function. We're going to look at two different forms of polynomial functions. One is factored form, which is very similar to our quadratic factored form, except the degree will be higher than a quadratic. And the other form is standard form. So that's, when you've multiplied out factored form. Now both forms are useful for different reasons, but let's go ahead and define some of this vocab before we talk about what they're good for. The first word we're going to discuss is the leading term. The leading term is the term with the highest degree. Okay, a lot of people see leading term and think it's the first term. It is the first term if your polynomial is in order in standard form, but let's say these two terms were switched. This would still be the leading term because it has the highest degree. So it doesn't necessarily mean first term. It means highest degree term. So our leading term would be 5x to the fourth in this case. The lead coefficient is the coefficient on the leading term, so that would just be the 5. And just as a reminder, degree is the highest exponent in that polynomial. So the highest exponent term is 4, so this is a fourth degree polynomial. In terms of defining our degree with a word, we know that a second degree polynomial is quadratic. A first degree polynomial is constant. It's a linear function. This kind of function is called a quartic function, and cubic would be a third degree polynomial. Okay, so there's a couple other words that we're going to go into discussing, and all of these words are going to help us sketch graphs eventually. So the last two words are zeros and multiplicity and constant term. The constant term is probably the easiest one, so the constant term is just the one that has x to the 0 power, which remember anything to the 0 is just 1, so that's why it's not written there. So the constant term is the one without a variable, which is just negative 40 in this case. And the zeros in multiplicity. So the good news about our polynomial functions is they function very similar to our quadratic functions. If you have a polynomial in factored form, you can use the zero product property to find all the zeros. So let's say that this equation equals 0. In order for that to happen, either one or multiple of the multiplied terms would need to equal 0. So either this equals 0 or this equals 0. So you get x minus 2 cubed equals 0, or x plus 1 equals 0. Now this one's a little bit easier to solve. You just subtract 1, you get x is negative 1. This one is a little bit different because you have that cube. So in order to undo a cube, you would do the cube root of both sides. Now if you do the cube root of 0, though, it's just going to be 0. So not that you can ignore the cube root, but it's not going to change the problem. So our 0 still is 2. So in this case, we have two different places where this function will cross the x-axis, at negative 1 and 2. Now, we can plot these and go ahead and sketch a graph, but we don't really know what this function looks like. So this is where our second objective comes into play today. So we're going to talk about what's called end behavior and multiplicity. So by the end of this video, you will be able to sketch the graph of a polynomial, given the zeros, the end behavior, and the multiplicity. This will kind of help us figure out, if this graph crosses at negative 1 and 2, what happens everywhere else? Does it go up and down, or I'm not sure yet. So we're going to use this site to explore. Okay, so to talk about zeros and multiplicity, we're going to look at this Desmos interactive here. So let's say you have a polynomial. We don't know the lead coefficient, so I'm just going to call that an a. I can change a to whatever I want it to be. And I don't know what degree this is. So right now it's set to n equals 2, but I will change the degree and see what different things can happen. So I can just kind of play around here. You can kind of start to notice some things that are going on when I change those numbers. Let's look at a few specific examples. Okay, let's say n equals 2. This is a parabola then, x squared. As your a changes, what happens? Hopefully you know from our last chapter that if our a is negative, it's going to reflect the parabola over the x-axis. If it's positive, it'll go back up and look more like our parent function. And that's when n equals 2. Now let's compare this to n equals 3. So n equals 3, the way the parabola changes, it was facing up on the left here, kind of like towards infinity, and towards infinity on the right here. The y values are getting bigger. But as soon as I change this to n equals 3, now these y values are going towards negative infinity, and these are going towards positive infinity. So instead of facing up, up, we now have down, up. Now if I change the a value, positive doesn't really change much except the width. Once it switches to negative, it's going to reflect over the axis as well. So that's very similar to a parabola. A negative number, a negative leading coefficient, we'll use our vocab, will change the direction or the reflection. Okay, so let's see what happens when n equals 4. Now our parabola has changed from down up to up up. And if I change our a, again, it's going to reflect just like a parabola. N equals 5, again, we have a down up. And as I go negative positive, it's going to reflect again. Let's try n equals 6. So now it's down down, it's positive, it's up up. So it's kind of like a parabola, or kind of like x to the 4th. And n equals 7 is down up. So hopefully by exploring this, you've looked at some patterns, and these patterns are called end behavior, or will help us sketch the end behavior of the graph. So I'll talk about this in a second, but end behavior is just really what's going on at the ends of your function. And this isn't really a precise definition, but it's easy to understand. So where is your graph pointing at the ends? That's the easy way to say it, at least. And of course, I'm going to give you the real definition. So let's say you have a polynomial function. We're going to call it p of x. It can be any polynomial, so that's why you see all these variables here. I didn't assign any numbers. So the coefficients are just the an's, and it's just calling each one something different, so we don't have all the same coefficients. And then you have a bunch of variables. So you'd start with x to the n minus 1. So like if x to the n was x to the 4th, x to the n minus 1 would be x to the 3rd, x to the n minus 2 would be x squared, all the way to just where you have like a single x and a constant. So this is just a way of writing a generic polynomial function. So again, it's calling the coefficients an minus 1, a1, all the way to a0. These are the coefficients of the x terms. And it's just saying they're real numbers, and the exponents are whole numbers. So you can't have like a 1/2 exponent, because that would change the polynomial function. So what we just looked at is called the leading term test. So in order to figure out what the end behavior looks like, it's enough to just look at the leading term. So again, a was defined as our leading term. If our leading term is positive or negative, things happen. And so a was our lead coefficient, excuse me. Our term is the whole thing. So x to the n is the rest of our term. So whether that number is even or odd will change what happens. So look at the even numbers, 2 and 4. They both point up, up, the same direction. Whereas our odds, they're going in opposite directions. So that's down, up. And so is x to the 5th is down, up. Okay, so let's formalize this into a definition. If n is even, so n is the exponent again, and an is greater than 0, so that's the lead coefficient. And I like to relate this to something like a parabola. So we have an even exponent, and our coefficient is greater than 0. It's going to look like a parabola, something like this. So our ends will be up, up, facing up. Or as your x values go to negative infinity or positive infinity, your y values will both go towards positive infinity. So they're going up forever. If n is even and the lead coefficient is less than 0, it'll be down, down. So looking at patterns, coming up with a theme. Now if it's odd, the odd functions went in different directions. So we had a down, up. So that was if the lead coefficient is positive. So we'll go down and then up. Or if the lead coefficient is less than 0, we'll go up, down, because it'll reflect over the axis. So to remember this, I think about a parabola for the even ones. If the lead coefficient is negative, our parabola would reflect and be down, down. And I think of a cubic for n being odd. So a regular cubic with a positive lead coefficient looks like this. And if we make it a negative coefficient, it would reflect and look more like this. So it'd be up, down. Now, when I say up, down, or down, up, or whatever, I'm really talking about the left and then the right side. So reading it like a book. Now, there's another thing called multiplicity. The multiplicity is how many times the 0 is counted. So let's go back to that original problem I was looking at. Really, you have x minus 2 and x plus 1 as your factors. So our different zeros were negative 1 and positive 2. But this positive 2 was counted 3 times. there are technically 3 x minus 2's in this polynomial, whereas there's only one x plus 1. So the amount of times it's counted is actually going to affect what our graph looks like. And there are 2 general rules, which I'll show you in Desmos as well. So if the degree is even, so something like x plus 2 squared, or if the degree is odd, so something like x plus 2 cubed, they will look slightly different on the graph. If it's even, the graph will be tangent at that point. The graph will be tangent to -2, for example. At that point. And if it's odd, the graph will cross at that point. Graph will cross through. And let's look at Desmos to kind of reinforce that. So I'm going to ignore this graph for a second, and I'm going to look at this one here. So I have 2 different zeros. I just picked -1 and +3, and I have sliders to represent the 2 exponents. So let's zoom in a little bit at each of these, starting with the 0 at 3. So that's my D. So what happens is I make D even or odd. So right now D is even, so D is to the 4th power, so it's just going to be tangent at that point, not cross through. But if I make D odd, now that 0 is going to cross through here instead of being tangent. And you can test a bunch of different values. So if it's 8, it's even, it's tangent, whereas if it's 9, it's going to cross through. And if you want to just kind of confirm that, I can take a look at -1 as well. I should zoom out a little bit. So at -1, right now C is 2. If I make it 3, it's going to cross through. If I make it 6, it's just going to be tangent and not cross. So between the multiplicity and the end behavior, you can get a really nice sketch of the graph. Oh, and the zeros, of course. So let's go back to the original equation we were talking about. We already know our zeros are at -1 and +2. Can we figure out the end behavior? And can we figure out the multiplicity? So let's start with end behavior. We already said our lead coefficient is 5, and this is a 4th degree polynomial. So 4th degree will mean it's an even degree, which is kind of like a parabola, where it will either go up, up, or down, down at either end. Since the lead coefficient is positive, it's going to be like a positive parabola where it goes up, up. So I know my ends look something like this. I'm going to erase the rest of this, so we're just looking at the function. Now in terms of multiplicity, I need to know what happens at these 2 points. Is it going to be tangent or is it going to cross? So the multiplicity at the 0, 2 is an odd multiplicity. The multiplicity would be 3 because it's counted 3 times. Same with the -1, except it's still an odd multiplicity, but it's counted once. So there's just one x plus 1. So that means they're both odd. They'll cross through at those points, not be tangent. So if I want it to cross through, it's got to start up. I don't know exactly where, but again, I'm just trying to sketch a function. So maybe it starts over here. It's going to cross through. Then it's got to cross through again and go up. Now, I'm just sketching it based on zeros, multiplicity, and end behavior. I don't know what's happening all up in here. I don't know how wide it is. I'm just getting a sketch. That's enough for now. Eventually, we'll figure out, what else can I do to make this more accurate? Can I plug in some points? Can I find a y-intercept? The more information you know, the better your sketch is going to be. But by the end of this video, you should be able to just look at the polynomial function, even if it looks as complex as this, and figure out the end behavior, multiplicity, and zeros. And you should be able to then sketch a graph. So please come with questions. Have a good night.